Okay. Sorry, thanks. Okay, I'm going to start.
Yes.
Funny feeling. Okay, so I went through this, the CIGAR algorithm last time. Do you have any questions about it? So the main, to recap the summary, so there is the first step where you construct n hat, okay, n cap, which is, what I call is the initial abstraction, and there are, a couple of ways where the paper discussed as to how to construct. We will get to that towards the end of last lecture. I gave you something. So, I mean, I did describe very quickly, and I will give, I will revisit it, giving a little more detail. Once you construct the initial over approximated abstraction, then you verify the property. So this is a property independent, property dependent abstraction, as you saw. So if the property is a validity check. So you take the negation and you check if it is unsat. If it is unsat on the over approximated abstraction, then you can conclude that it is also unsat. Okay. On the original network, and therefore you can return unsat. Else, you extract a counterexample. So a counterexample to unsat is there is a satisfying instance that, since in over approximations, that could be either a real counterexample or a spurious counterexample. So that is what you have to check there. Okay, if C is a counterexample for an then that's what you check there. You extract the counterexample. A counterexample is, it'll give you an input, okay? The input is an actual input for which the property is, is not unsat, that is not valid. The property is not valid for some input, and it will give as a witness the input. Okay. Now you have to simulate that on your original network to simulate it to see the actual output that you get is indeed violates the property or not. Okay. If it does, then it is a real counterexample, and so then you can conclude that there is a real violation on the of the property on the original network. Otherwise, you refine the then you conclude that the over approximation is too coarse, too imprecise, and therefore you execute a refinement step. Okay? Where which really consists of taking one merged node and then splitting it by extracting one original node and then putting it back into the thing. Okay, so that's this loop. So today I will look at in a little bit more in detail the refinement step, as well as the two different ways in which the paper discusses as to how you could compute the initial abstraction. Okay, any questions here? Okay. Yeah, okay. As I said, okay, one way, of course, there are two ways. The first way is kind of fairly simple. You can merge up to saturation. That is, look at each layer and then you merge all the nodes that have the same attributes. As I said, you can only merge nodes with which have the same kind of attributes. There are 4 different possible attributes, so you could merge them all, okay, into one and use that as the initial abstraction. If that's the case, that has maximal merging. So each layer then can reduce to can have at most 4 abstract nodes, like at most 4. Because in some cases there may not be any nodes with any attribute, therefore there'll be at most 4. So that will be the smallest thing that you can get. Instead, the paper also proposes something called an indicator guided abstraction, which I will discuss today. That is based on sampling the input space and kind of merge them such that they satisfy the original property, and then you merge only as many of the nodes until one of the property on one of those sampled inputs will become falsified, will become false. Okay, so that kind of a thing will be not as coarse an abstraction to begin with. It will be somewhat more refined. Okay. Similarly, so this is something that we discussed last time also. So this is the idea for splitting once again, okay, so the various heuristics that are used for merging will have to use the larger the difference between the weights on the incoming edges, okay, among all the nodes that get of like attributes that get merged into the same node, the coarser the abstraction will be. Therefore, the general guideline for merging is try to merge use that as a measure, so that you will reduce the imprecision as resulting from that. So you take the maximal value, among all the maximal values, take that pair which produces the minimal among all the maximal values based on the corresponding edges. Okay, so that is a rough idea as a criteria, as a measure to pick which two nodes you could merge first. In split, it is kind of the reverse. So once you have merged, say, a set of nodes into an abstract node V bar, now when you get a counter example which is spurious, there you have to decide which one of the concrete node, that is the actual node, the node in the original abstraction, to pick from inside V cap to put back. Okay. So notice that the counter example, where V and V hat are, V is the value on the counter example that the original network produces at that abstract internal node, and V cap is the value that is produced by the counter example produced by the abstracted network. Okay, so the measure or the measure which is used to come up with a criteria takes into account these two pieces of information. Okay, so you have to pick that V where the difference between these two things is maximal, because when you refine, you want to pick that node which refines as little as possible. Okay, so that you don't miss anything. So it will be the minimal there. And similarly, the edge weight, and you also look at the differences among all the weights on the corresponding edges. Okay, between V and V prime, you pick you look at the difference in that and try to come up with a measure that takes into account both of these things, so that when you refine it, you will refine it the most. Okay, and that's what these two. So these two details of how to construct an abstraction, an initial abstraction that is different from the abstraction to saturation, which is easy to implement, is something that I will discuss with a little bit more detail today. And just a minute. And the splitting heuristic also. Okay. So here it is. So all it does here is to okay, it has to find the best fare first. Okay, so it starts with sampling the input space into a set of inputs. Okay, and such that the property is satisfied on all those inputs on the original thing. So on the network. Okay, and then it iterates through in each hidden layer. It looks at each hidden layer. In each hidden layer that have among all pairs of nodes that have similar attribute, it picks that one, like I said before, a measure. So it kind of iterates through all pairs by looking at the difference, okay? The maximal, the difference between the weights on corresponding edges. And then iterates and then picks the one where the pair has its maximal difference among the corresponding edges is minimal, okay? It picks that pair whose the maximal value between any two corresponding pairs is minimal among all those pairs. And that's what it is doing here through these two loops, okay? By storing for each pair, after it compares, it stores what its measure, okay, is. And it has to, pick the pair whose the maximal difference among the, the maximal difference between any two corresponding weights is minimal. Okay, and that's what it does, and that it keeps, and then it merges that, and it keeps doing it in that order of those pairs until it, as long as it, the property is never violated on the abstract network. So each time it checks after it's merged if the property is violated, and it merges only as many pairs of nodes in each layer until the property gets violated. Okay, because there's no point in merging after that, because it would have you would get a spurious counterexample anyway if you had merged any further, and that is the approach that it that it uses. Now, so this is less imprecise, this thing, in somewhat, than in general, than what you have when you abstract to saturation. Okay, so that is the idea here. Okay, so any questions? Can you speak up? It is less imprecise. What does that mean? Which means that, see, whenever you use this abstraction in node merge, it is, what does it happen? It always produces, the way I went through last time, it always in a monotonically increasing abstraction. So for the same input, it'll the node merged abstract the abstract network will give something, a value for this for the same input, something that is larger than what the original network produced on the same input. So in that sense, it is a coarse. Okay, so what I meant was that the abstraction that you get which is the coarsest abstraction, the one that produces on any one value the large the difference between the original output and the abstracted output is the largest. Okay, that is a measure of coarseness. Okay, so in that sense, this way of computing the initial abstraction will be less coarse, okay, than the other one. Okay, so it is in that sense this can be used as a, um, an initial abstraction. Okay, uh, yeah, and it is based on just sampling some set of inputs, and I'll use that as a guide. I mean, you can use some uniform, sampling by uniform distribution, or based on some intuition that you have, on some, distribution that uses some notion of coverage. You could sample that thing and then use that as a guide to see. I will try and merge them as only as much as possible until the property gets violated. Okay. Okay, so that is one, initial, the two ways the paper discusses, two ways in which to construct the initial abstraction. This is one, and the other one is up to saturation. Yeah. No, 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 no. So you remember that the nodes were tagged as either being plus or minus based on whether they all have. Okay, so we split it, the original network, I mean the nodes in the original network, so that every node always had weights. The outgoing weights were always positive or always negative into plus minus. And then among them we also tagged those things which were increasing node versus decreasing node. Then you get four possible taggings, and that's what I mean by the attributes. Yes. Yeah. Okay, so here uh, the splitting is guided. Okay, the splitting. What does splitting mean? Okay, so you get a counterexample. You check if the counterexample is not real. So then it is called spurious counterexample. You have to use that information somehow to select for each abstract node. Each abstract node consists of a merge of potentially four different nodes in your original abstraction, I mean original network, that have the same attribute. Now if you have got a spurious example, now you have to refine. Refinement means you have to put back one of the nodes that got merged into the same an abstract node, the one of the concrete nodes. You have to take it away from that and then do it. Like for example, so if I'm taking too much, so yeah, so here these two got merged. Okay, and suppose I check the property on this, it got violated, but it was a spurious counterexample. Now you will have to refine it to, by splitting this thing. The question is, which node will you pick between these two that got merged to put back into the thing? The idea is to pick that node based on a certain measure that will reduce it the most. Okay, it'll make it more precise the most. The best way to do is to pick that node which.
Can you hear me now in the meeting? Okay, can you say something? I can't seem to hear anything on your end. Hello, can you hear me? Hello, hello, hello. Okay. So yeah, but I can't hear you. It seems. I don't know if it's on my end. Yeah, I tried that a couple of times actually. I'll do it once more. Can you hear me? I still can't seem to hear you. Okay, this is bad. Uh, yeah, I cannot hear you. I cannot hear. Can you hear me? Hello. I still can't seem to hear you. Okay, yes. So yeah, you can proceed with the rest of the Maraboot talk. Yeah, hi. I s- it's a I don't know if you can hear me, but I can't hear anything at all still. Uh, we can try and fix this, but if it seems hard, we can also I can share you a Teams link and we can maybe just continue that way. I can record things on my end and share the recording later on.
So I think the
Oh,
problem.
now I can hear. Now I can hear. Yeah, yeah.
Oh, now you can hear me? Enachi?
Yes, yes.
Huh?
Yeah, yeah, yeah. I can hear. I can hear.
Oh, okay. Okay, good. Okay, so Diganta,
Mhm.
finished the part of the paper in which I discussed both the two heuristics that they use for constructing the abstraction. Okay,
Right.
abstraction to saturation, and that indicator guided abstraction where they sample the input space and then use that to merge nodes only until they see one of the properties getting violated, okay, to get a less imprecise initial abstraction. Okay, so and
Right.
similarly I did method to do refinement by picking the
Mm-hmm.
from Ritra here. So instead of his question was, and I thought that you could give your input there if you had any feedback. That is, instead of refining it by picking one node to put back at a time, which is a
Mm-hmm.
way of refinement. His question was, why don't you do a binary search kind of a thing, where you in one shot do refine it to some an abstraction which is half the size, where half the numbers are merged. Is that it is doable, okay, but you will have to each time construct the abstraction. That is one drawback.
Right.
You have experimented with this thing. That's why I wanted your feedback. What is your opinion?
Yeah, yeah. So I think the main thing that would be an issue with that approach is that, see, if you go to a very big abstraction and you want to check if that abstraction will work or not, now you need to do a solver query for that big abstract network, right? So if that solver query was at all feasible for you, then for that particular network, you don't even really need an abstraction in the first place, right? So really, the only so the only situation where binary search would be feasible is where an abstraction itself in the first place would not be needed, right? Uh, so that's why that sort of a thing doesn't work. Like if you go back to a big abstract, let's say where the half of your things are unmerged and half of your things have been merged in, if it is possible for you to run a solver query and get an answer for that, you might as well just start from there, right? And keep going higher.
Yeah,
Yeah.
yeah, that is one. And the other thing is here, you see, I mean, there is one disadvantage in this kind of a structural abstraction, especially since they, split four ways. Okay,
Right.
before actually doing the merge. Therefore, most likely the halfway point is still a a large abstraction. If the refinement, this method would succeed at all, it has to be somewhat very close to the
Yes.
end. But nonetheless, Diganta, we tried semantic abstraction, maybe I'm getting a little bit overhead. Maybe we can revisit this. I'm going to ask you to say a few words at the end once I finish covering the experiments section from the paper. A little bit about the semantic abstraction that we did. I know not the whole thing. Just give a teaser, since that is one of the papers that is on the papers list to
Yeah.
discuss.
Yeah. 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 So yeah, I'll talk about that in a bit.
Take it up
You know.
there, along with it, because I thought that you do try doing some binary search there. I don't know. I might be wrong.
No, I mean, I don't think it's. I mean, yeah, maybe what I'm doing is binary search is maybe not a good way of talking about that because,
Okay. Yeah.
yeah, I
Yeah.
mean, essentially we kind of end up boiling it down to a gradient descent based search, which at that point, I mean, we're not even looking at the order of things directly anymore. So Yeah,
Okay.
it's I think a bit different. Yeah, but I'll maybe talk about it in very briefly later on when you're
Yes,
done.
the Ritra had some wanted something to add. What was that?
Yeah, I'm not able to hear the audience
I
questions, by the way. I
know,
mean,
I know.
that's the
It's,
yeah.
in a yeah, here it's a big classroom, okay, and they are we are sparse here, and they've
Yeah, that's completely fine. Yeah.
because I think the NK hall there is cameras hanging all over the place, but not so here. I think Ritra was saying was okay. That is a feasible one. What he's saying is instead of doing strictly putting one node at a time back,
Mhm.
what he's saying is maybe you could consider putting two nodes, four nodes, okay, like that. Each time
Yeah.
increase putting back more number of nodes, okay?
Right. Yeah, that is something that we do, in fact. I mean, in fact, if you look at even the implementation of this paper, if you look at the GitHub, the code in the GitHub, what they do, even though they say that they're going to put back one node at a time, what they do is actually put back 50 nodes at the same time. So
Oh,
so
I
that is
see.
indeed that is indeed what they do.
Yeah,
Yeah, yeah,
makes sense, okay?
yeah.
This is somewhat like an approximation to this kind of binary search. Yeah, yeah.
Right. I mean, yeah. I mean, in the sense that you might skip over some efficient abstractions, but then again, you're not spending a lot of time just keep on constructing small abstractions and checking them which fails and so on, right? So it's
Yeah,
like, yeah.
yeah.
I think they tuned this a bit based on the experiments and so on. But yeah,
Well,
this is what we found. Yeah.
Marabou, does it have as a parameter about how many nodes you want to put back in each refinement step? Okay, that is worth looking.
No, I think they are kind of they have some. I mean, it's not nicely exposed via some API, unfortunately. The I mean, I think it's hard coded to certain numbers which work well, basically.
Okay.
Which if I remember correctly, is something around 50. Why they choose that particular number, I don't know. Maybe it's based on the kind of benchmarks that they have
Okay. So
experimented
let
on.
me
But
let me move on because we won't have much time for even if I cannot get to it next time you could do, but I want to really spend some time giving your thoughts on the list of papers. So I'll
yeah,
take 10 minutes maybe at most 10 15 minutes to 10 minutes maybe to wind up the experiment section because
right.
that's important for them to understand and appreciate.
Yeah,
For that, you can talk about the papers list. Okay.
yeah,
So,
yeah, yeah. Sure.
yeah. So experiments, it's the same benchmarks that is used as what was used for Reluplex. It is this ACAS XU benchmark. Like I said, it had 45 DNNs where each of them, produced for some set of input scenarios of the aircraft positions. Okay, and for different set of input scenarios, it used to give each of them gave certain advisories. Okay, all that is thing, and that's the rough size of each of those networks, 300 neurons, across 6 layers. So when they were after equivalence transformation, so the networks had 1200 neurons. And the properties, as I described last time, are two kinds of properties. They were correctness, what are called correctness properties, which formalized that the DNN gives the expected advisory for inputs that meet that are that correspond to certain specific input scenarios of the positions of the two crafts. And here these properties, what was expected was specified based by consulting some experts in the domain, and that's how it was formalized. And in the previous in the Reluplex case, I showed you like a graph of colored graph which showed what the expected things advisories were for different input scenarios. That was the first class of thing, and the other class of correctness properties was that it doesn't give unnecessary advisors. That is, if the graphs were far apart with no chance of collision, then it would give COC, which is clear of conflict, kind of an advisory. But the other set of properties were robustness properties, okay? As I explained before, so robustness properties are of the kind that if you sample your inputs and then simulate the inputs and then see what how they are what kind of advisories each input, you select one input and then you perturb that input to see how much perturbation it can tolerate before it flips that decision. It gives a different advisory, that kind of properties. So it's the same thing. So that was verified using ReluPlex, and they wanted to compare this with the abstraction. The goal of the experiments, I'll show the figures from the paper in a moment, but this is a summary. The goal of experiments were actually three kinds of experiments that they ran. Experiment one compared each of them compared performance of verification with abstraction and without abstraction. Okay, the first one was comparing by vanilla Marabou, I mean just the ReluPlex without abstraction. But you could use any engine. Okay, this abstraction technique is kind of orthogonal to what verification engine that you actually use underneath it. You could apply this abstraction technique with the underlying engine being Z3 as well. But they did, the vanilla part was ReluPlex. Okay. What performance is measured, the time, okay, it takes. So each benchmark means for each benchmark is they chose some subsets of one of more of those DNNs, and for each of them they verified a whole bunch of 12 properties or so. So each benchmark corresponds to this pair. For each benchmark, which property was. And then there were like 900 different combinations that they tested various DNN networks on different properties. So, and they measured the time and the number of instances where one of the approaches timed out. Okay, they gave a timeout. They ran the verification for up to 20 hours on each of these, on each instance of your input, benchmark. And they also measured, how many among those things that they ran the experiment on timed out. Okay, in each, for each of the two things that they were comparing. Similarly, they did as I told you that there you could there's a choice of the way that you select your initial abstraction, either doing it to saturation or this indicator guided abstraction, and they did the same experiment by using these two different kinds of initial abstraction and see which one fared better. And and then for robustness properties. Okay, so there were special experiments done for robustness properties as well. So I'm going to show you what they have given in the paper, the scatter plot, to give you an idea of how well yeah, I'll first show you this one. Yeah, these two on. This is comparing Marabou with abstraction and without abstraction. So on the x-axis is called scatter plots. Each dots, blue or red dots, is the outcome of running that benchmark property pair, the input instance, using Marabou with abstraction, that the time is shown on the x-axis, for this tool, and on the y-axis is vanilla Marabou. So obviously, if there are more, the red ones are for which that, so if there are more dots, blue dots on the above, so this is where the both, would perform equally better. So if there are more things there, the Marabou with abstraction would perform better, correct? Okay. What they say is, it is in summary, okay, there were, am I right? Yes. Correct. So, there were, they ran about 9 out of 900, I think 805, all but 100 on 100. Actually, the vanilla abstraction produced more, it completed successfully more times than Marabou with abstraction. Okay, out of the 900, about 805, this thing did, and about 80 to 90 more, it was able to complete it, the vanilla abstraction. But if you looked at the time for which those things were Marabou with abstraction as well as the vanilla Marabou finished successfully, the time that was taken by with abstraction was much less. Okay, so the average time was significantly less. That is that was the outcome. Where it succeeds, it turned out to do much better. No. Here, no, I'm sorry. I'm mixing up the experiment of robustness properties to do with this thing. So here it did, as you can see. No, I'm sorry, I take it back. This is the first experiment where they were running it on correctness properties. Okay, there this uniformly did better, as you can see. As you can see, there are more things in which the vanilla Marabou timed out than the ones in which the one with abstraction timed out. Okay, so here it did quite better. It was here where you can see this was on not the correctness properties, but on robustness properties, okay, which compared with perturbation. Yeah, so there it seemed like this was had more time out, okay, and you can see that the vanilla Marabou did complete on all the input benchmark instances. But among the ones in which the abstraction Marabou with abstraction did terminate, it seemed to do better in terms of timings. Okay, that was the conclusion. So overall, it seems like abstraction does seem to work. So this one was comparison when they were using initial abstraction versus this one is the indicator guided, and this was this is abstraction to saturation. So there they conclude that at least for this class benchmark, saturation itself did quite quite well, okay, in most cases, which was a little bit surprising, but the indicator guided abstraction did not help as much. I think that is the takeaway from the experiments. Okay, so do you have any questions? Yeah. Yeah, so I'll, do you want to add your inputs, Diganta, if you could still hear us?
Yeah, I can hear you. Yeah.
First on the experiments, what you think of these scatter plots, your observation on the scatter plots, and then a little bit more as to the direction that one can you have pursued in terms of.
Right. Yeah. So I think, I mean, one of the things is that if you see that, so they're getting some improvements in these catapults, right? But there is a few interesting things. One is that you will notice that in the experiments, this is something that they mention as well. In some of the cases, even though the final network that they get is actually slightly larger than the original network, they are still able to get a smaller time on Marabu,
Mm.
right? So I think this is an aspect of the whole space of structural abstraction that has been relatively underexplored, which is that how does, is it really the case that if you keep making the network smaller, the time that a solver takes will keep getting smaller proportionally, or is there something more about the structure of the network that will affect the time that a solver like Marabu will take, right? So this is there. But also, I mean, in a large number of cases, if you see, uh, you know, the kind of so when we rerun the experiments, in a large number of cases, the uh, it would actually either go through when you do this abstraction loop on very small networks, or you would have to keep refining and until you get to a very large network, and then you kind of ended up timing out, right? So there is really, it's not really the case that there is kind of large or a uniform distribution of the sizes of networks at which the proof goes through, right? So while there is this abstraction loop where you keep on adding keep on refining and adding back more and more nodes, in most cases what we found is that either your original fully merge until saturation is going to go through, or your you have to refine until you get a fairly large network. And I think that might be one reason as to why this indicator guided abstraction doesn't seem to work very well, because in the indicator guided abstraction, you're somehow in cases where the uh, where integrated guided abstraction will not tell you that okay, the fully saturated one will go through. In those cases, you'll have to anyway kind of refine until the uh, original network, right? So it's like the indicator doesn't really give you too much. So based on all of these kinds of observations, what we were kind of thinking is that somehow the space of possible merges is being underexplored, right? Like what could be one reason why it's either the case that if you merge everything, it's fine, or you keep unmerging and you end up going back to the whole thing, right? Because the path that one is taking when we are unmerging nodes one at a time, maybe that is really not exploring the space of all possible merges adequately. And that was kind of the intuitive hypothesis that we had when we started sort of exploring this. And yeah, so I mean, we did a large number of works exploring various, we explored various directions, but
Yeah.
finally what seemed to kind of work for us was that we were able to sort of uh, rewrite this whole merge process as something that will be parameterized by a bunch of real valued parameters. So instead of just saying that, oh, I'm going to select things and I'm going to select these ink nodes and merge them together and leave these ink nodes unmerged, we can now have some parameters, which real valued parameters, which will control to what extent we are going to merge things together, to what extent are we going to leave things. And you can have situations where you can actually kind of come up with an abstraction, sound abstraction, where you can say that I'll merge 25% of this guy, 75% of that guy, or 70% of that guy, and 5% of this guy, and something like that, right? So we're able to come up with an abstraction of that nature, and then sort of this whole searching through the space of abstractions becomes a problem of finding appropriate values for these parameters, which we can then use gradient descent to solve. And that was kind of the work that we have been doing for a while. And
Yeah,
yeah.
so maybe yes. If I could paraphrase what you're saying, your abstraction is less structural and more semantic, huh?
Yeah, much more structural and more semantic, and that was kind of the intuition behind this, right? I mean, if we are indeed under exploring, what is it, what kind of information can we leverage to explore more, right? So if you look at here, the only thing that they're looking at when they're removing or putting back a concrete node, when they're unmerging something, is just they're looking at information based on one counter example, which is kind of I mean, it's some amount of semantic information, but very little, right?
Oh, okay. So you could look at
So
simultaneously multiple counter examples and then learn from that to do a
yes,
more
yes.
effective refinement, huh?
Yes, exactly, and that is how we can explore a larger amount of the space, right? So there is two aspects of it. One is, of course, being able to explore a larger amount of space, but also this parameterized merge that I'm talking about. I think, I mean, this is one of the papers that is there in the list.
Yeah.
The parameterized merge is also going to be more expressive than any of these things, right? So it's a combination of a more expressive, when I say expressive, I mean as a as what kind of possible abstract networks can you reach by doing some kind of merge. In
Yeah.
that sense, it's more expressive. So you have more expressive merges, and you have a better search based on more semantic information coming from
Yeah.
more counter
So,
examples. Yeah.
Diganta, so I think in the interest of time, so at least about
Mhm.
it about 10 minutes. I think some of them will have to, you have to have a class to attend at 5 o'clock, some of you, I guess, now. So,
Right.
only one small observation that I made, that I would make before, because we will get an opportunity, since when, if some of them will have some of them pick some papers on abstraction. Okay. So I
Mhm.
want to hear from you about the papers list. Can we switch over
Right.
to that to spend 10
Yes.
uh,
Yeah. 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 Absolutely.
that?
Yeah.
And I'm sure that I'll only have 10 minutes. Okay. So, and but even if you want to leave, we will have to, that is something that we will be discussing next week also. And
Right.
somewhere by the end of next week, I want the paper assignments to be finalized. So after hearing, our own thing, and you read, as I said, you read some of the abstract and so on, and then you will have to get the thing, done.
Yeah.
But
So let me.
yeah,
Uh,
I'm going to show that. Okay, so but for me, see this one here. Why do you think? I mean, just want a quick question, okay? Because I was thinking, why do you think that there were 900 different benchmarks? Okay,
mhm.
now, the vanilla marabou, this is a question that I'm asking to the class. Let's say I want to hear them. See, it completed all 900 of them, okay? Whereas with abstraction, it failed to complete some 80 of them. Okay, it is true. The positive spin on that is that when it completed, it really completed it much faster. But why do you think that it did not? When the original, Vanilla Marabou did manage to successfully complete, this timed out. Why do you think that? To me, that immediately was surprising, but then I thought about it, and then it is kind of understandable. I mean, I feel that there are two reasons. One could be two reasons. One is, I mean, you're doing one small steps of refinement. Okay, there are too many refinements, and you're running the engine so many times, nah? So the
Mhm.
times the if the number of refinement steps dominates in your other thing, each time you're running, maybe on a smaller network, which progressively gets bigger and bigger, and eventually the more number of refinement steps, it even gets bigger than the original network, okay? And therefore the time accumulates, okay? The number of times
Yeah.
to run the thing. So if it succeeds, it has to succeed for a small number of refinement steps. Only then it'll do. The moment you go beyond a certain number of refinements, your thing is potentially likely to explode. That might be the thing. Okay, so Diganta, I know that so you have 10 minutes to
Can I
sit.
share screen?
Yeah.
Shall I share screen?
Yeah. Please do. Okay, I'll make it
Yeah.
the
So can you? Yeah. Yeah.
that's
Can
the
you give me
best
the
thing.
permissions? Yeah. Yeah, and I think yeah, I mean that is exactly what we observed as well. By the way, I mean that is when we recreated this. So this scatter plot is something that can we recreated independently when we were exploring some of these things. That is precisely what we saw, that uh, for the cases that Vanilla Madabu wasn't timing out, but this guy was. It's just that we were some mid-sized network will take almost as long as the full-size network, and then you have multiple such calls. So
Uh, I should do here, no? Yeah, I got it. Already selected. Oh, this is here. Okay, you are co-host now. Please. Yeah, I think you won't be able to either. Yeah, I mean, I still want to give you 10 minutes. Okay, so I request patience from them. So you quickly give a thing, and then maybe you can elaborate a little bit more later on at the beginning
right.
next Tuesday when you will be going. Yeah, with Alpha Beta Crown. Yeah.
Correct. So I think, yeah. So I'll start with some of these relatively natural extensions of the node merging based abstraction methods. So I think if you're looking for a fairly easy, quick read, this is a interesting paper. Although I mean, in my opinion, what they're doing is also fairly. I mean, it's fairly direct. So what they're doing is they're going to do this kind of an abstraction precisely based on this index splitting merging, but then they're going to also tighten the abstract network slightly by doing some extra analysis based on interval propagation, right? So this is as I said, it's if you know this index splitting, you should be able to read this very directly. This is the paper that I was like. This is basically the paper that I was talking about. The work that we have been doing based on improving both the expressive power of the abstraction um, and using gradient descent for searching, right? So I think, I mean, of course, I'm highly biased towards this because it's work I'm involved in, but yeah, I mean, it's an interesting read, and I would be really glad to if you guys want to read it, and then we can have a discussion, right? Um, okay, so then there is this work, which is so there is another set of tools that we will cover that next week, which is this alpha beta crown. And I mean these set of tools. I mean, alpha beta crown is a single tool, but there's a class of tools based on similar techniques, and you can apply CGuard on those kinds of tools as well, which I guess would make more sense once we've covered those. So this is a separate line of kind of CGuard based abstraction refinement, different from the node merging one, used in a context of a different class of tools, right? And I think it's more tightly integrated. Like for example, here Marabu is kind of treated as a black box, whereas this technique, it does not really treat the alpha beta crown tool as a black box. Yeah, so semantic abstraction, I think for the sake of time, I'll skip, but it's interesting that they kind of give up on they either give up on being able to lift general proofs or on the kind of guarantees that the abstraction will be able to provide. But by giving that up, they're able to get more efficient abstraction. So this is a little less formal in the sense of formal methods, but also more efficient and maybe practically very useful and so on. Okay, so this is the kind of papers that we have on abstraction methods. Yeah, so feel free to take a look at these. Um, then the class of very interesting papers that we have really talk about some properties. So far we have been talking about techniques of how to verify networks. A question that is sort of, I mean, I assume I've not really attended a lot of the classes, I guess, but I assume that one of the questions that you might have is what do we verify, right? Like, what is given a network, what is a reasonable property to verify? And that's a hard question because it's not easy to come up with specifications. And this is so this question of what is a good property has been explored in several different settings by several different works. One class of this exploration is explainability, or really formal explainability. There is explainability from the ML perspective, which does not require any formal guarantees on the explanation provided. But here, when I say explainability, what I really mean is formal explainability, which means that whatever you call as your explanation, whatever that may mean, should be something that argues something precise and formal about the network, right? So I think the paper that you would really want to read here, or start reading from at least, is this one. This is the kind of the paper that kicked off this field. And what this paper basically does is that it shows that, okay, if you have an image classifier and you fix some pixels and you let the other pixels be whatever, and the network still thinks that this is the same class, then that can be called as an explanation, right? So for example, if I have an MNIST based classifier, let's say I've got an image with a 6 on it, and then it turns out that okay, if I fix these pixels and let all of these guys be anything, if even if for all of these possible images my network still thinks it is indeed a 6, then that is a good explanation as to what the network is looking at when it's deciding whether or not this is 6, right? So indeed the network is looking at this part of the image and not something in the background when deciding it's a 6, right? So it's very nicely argued in the paper, and very nice set of experiments and so on. So you can take a look at it, and it spawned a large kind of set of follow-up work. So this is a good follow-up work. It builds on it to give an anytime approximate algorithm, which is like so you can keep running this algorithm, and if you stop at any time, you'll have an approximate explanation. There's a good set of case. So there's another set of explanations based on a similar idea. But these guys, they really went ahead and collected a good set of case studies to kind of understand what whether this notion of explanation that was proposed in 5 and 21 really makes sense. And that I think is a very interesting read in 14 and 10. But yeah, so 5 is like a prerequisite for all of these things. This is also a very interesting paper, but it's kind of disjoint from the rest of the other guys. Here they really talk about kind of striking a balance. A Pareto optimality notion is brought in, where the balance is between how precise is the explanation. For example, here of course this is an explanation, and a more precise explanation can be maybe something that hugs sticks closer, right? So there's various notions of precision when it comes to explanation, and they argue that okay, I mean, if you're building a complicated formula that explains what the network is doing, you can make it more and more precise, and it'll talk about precisely what the network is doing. But as you do that, you lose understandability from a human readability point of view, right? So they kind of have a really nice discussion and analysis and exploration of this balance of out there, right? I would say that the explanation that they finally come up with is not very tightly formally linked to the model, because they're treating the model as a black box. So they're statistical explanations. They do have some guarantees, statistical guarantees behind these explanations nonetheless. So that way it's also different. But this idea of balancing precision and understandability is, I think, very interesting. Another interesting, kind of property. I mean, there's a lot of other papers out there, but I've just included some over here. Is this backdoor attack verification? So you know that you would often want to watermark neural networks and add a backdoor into neural networks, which will kind of, so if somebody steals your network and let's say pirates your network and hosts it on their site, then this backdoor will sort of be a dead giveaway that that is really what has happened, right? And then the question is, can somebody really make some small changes to the network and remove the backdoor? Or can we detect whether a backdoor is there in the network or not, right? So can we formally verify that a backdoor is going to be stable, right? So if we do some small changes to the let's just add some small amount of noise to the image or something like that, does this backdoor behavior go away? And this is something that is very interesting.
Yeah,
That
just one minute.
yeah,
So we're getting very close to 5. So any of you
yeah.
have class at 5? You have to leave. Okay. Is there any specific thing that you're looking at that you have any questions? Let me turn
Yeah, I think that's a good idea. I think, yeah, maybe let me zoom out a bit and.
the back door. Okay. Yeah. This is, Sai Sasank. Okay.
Mhm.
Oh, yeah. So you have like 3 minutes. So I guess, I mean, anything specific that you want to ask about backdoor verification before you make the choice that you could answer? No. So you are veering towards backdoor verification. Okay. So I think what you should do is say
Hmm.
2 sentences, Diganta, and then finish up. Or what
Yeah, sure.
we can continue
Uh,
next Tuesday. Why rush it? Okay.
no, so let me maybe say two sentences and we'll continue anyway if that's
Yeah.
okay with you. Yeah. So okay, I mean,
Yeah.
the other works out there, I'll just read out kind of the bullet points. There is a very interesting set of works which actually looks at camera-based autonomous vehicles and how one can verify neural networks in these autonomous vehicles. They do various kinds of simplifications because it's a very hard problem, as you can imagine. But they're like, okay, here is a car in an environment. Can you make sure that this will never collide? So that's very interesting. Of course, there is a lot of work for LLMs for verification, since this is a course on intersection of formal methods and machine learning. This is the other way around, using machine learning for formal methods. So using LLMs for verification, which is, specifically program verification, a lot of interesting works. And there is some works on formal aspects of reinforcement learning, right? So can we make sure that reinforcement learning agents are safe? And the main interesting way of doing it is really shielding, which is to figure out safe regions in which the RL agent can be limited to, and then we can have some guarantees that, okay, whatever the RL agent decides to do, as long as it's within the safe region, the nothing catastrophically bad will happen. Yeah, so that was my three sentences, and then we can
Yeah,
take
I think we will
questions.
talk a little bit more about it. The last two categories are somewhat different than the first two categories. And the first two categories
Correct. Yeah. Yeah.
closely related to neural networks, and they talk about verification the way that we have discussed so far, whereas the other two are somewhat different. The way, okay, so the LLM is, it's more an application, how you use LLM to do certain things that are useful in verification, but doing it in such a way for language translation or to discover invariance, etc. But use it as an aid to get to do it in a verifiable way. Okay, that's what. So there is commonness. I mean, the thing that is common of all these things is they're all sound techniques. Okay, in the sense when they say yes, you could rely on that. Okay, maybe except for the semantic abstraction thing, they do certain guarantees. Correct me if I'm wrong, Diganta. I haven't read those papers, but they do guarantee, but not in
Yeah, yeah, they do guarantees,
on
but it's
some
slightly weaker.
data sets, right?
Yeah,
Uh,
yeah, yeah.
yeah. So, but the last two are quite
So
interesting.
this is finite data
So
sets, and
they
yeah.
are a way to ensure safety of RL in the RL thing. But the other set of papers is how you use RL to do testing or to do certain things in a way the specification is clear, and how you decompose the thing. So there is this notion of how formal specification or formal verification can be used. Within that framework, you can do certain interesting things. Okay. Yeah, I mean, we will. I mean, like I said, next week to lectures, we will, at the beginning, we will definitely, and you will have to come up with questions too, based on some things that you will read, but you haven't been able to decide. So I'd like you to take the next step, plunge and get your hands and feet dirty. So even if you can shortlist something, but you don't know how to decide and you want to get it, that's what I want you to do. Okay. Uh,
Right, right.
yeah.
I
Thank
mean,
you.
reading abstracts maybe is a good idea. Like there's
Yeah.
some
So, I mean,
important papers.
the rest of the things, I mean, with this time slots for next class, etc. Since Diganta will be here, we have to do it here. That means then I'll have to adjust the time slot. So next week class, wait for announcement as to what the thing is. Thursday, this thing is available, but the other two other class will have to be. Sorry about that. Okay, so go ahead. Yeah, yeah. Thank you.
Yeah, thanks, everyone. So that's it from my end as well. I'll stop sharing.